Look at this, a country of just 2 square kilometers, hemmed in by France on every side, and on the south, nothing but the Mediterranean Sea. Monaco has almost no room to breathe. It's the second smallest country on Earth, smaller than Central Park in New York. And yet, right now, it has more billionaires per capita than anywhere else on the planet. The demand for space here is insane. The price per square meter of property is insane. So when you run out of land, you build more land. This is Mareterra, a brand new district, a brand new peninsula, 6 hectares of land that did not exist 10 years ago, literally manufactured in the middle of the Mediterranean Sea. It cost 2 billion euros. It took 10 years. It involved 300 international companies and more than 4,000 workers. And it expanded Monaco's national territory by 3%. That might sound small, but for a country this size, creating 3% more territory from scratch in open water on top of an active seabed between 2 protected marine reserves, that is one of the most complex feats of civil engineering ever attempted in the Mediterranean. To understand why this project exists, you first need to understand Monaco's geography problem, and it is a genuine, hard constraint. Monaco is a city-state perched on the French Riviera, to the north, west, and east, France. There is no border available for expansion. The mountains physically box it in. To the south, the Mediterranean. That's it. Those are the only 2 options, up or out to sea. And they've been doing both for over 150 years. The first land reclamation here dates to 1865, when fill was used to build a railway connection. By 1880, 5.5 hectares had already been claimed. Then came the big waves. Under Prince Rainier III, known as the Builder Prince, Monaco underwent what historians call a territorial revolution. Between 1954 and 1961, the Larvotto district was extended into the sea, creating an artificial beach. Then, from 1965 to 1971, the entire bay of Fontvieille was drained and dried, an industrial district conjured from nothing. Those 2 projects alone grew Monaco from roughly 150 hectares to 202 hectares, a 20% increase in national territory. Today, more than 25% of Monaco's total land area is reclaimed. It literally didn't exist before engineers put it there. But here's where things get interesting for engineers. Each successive reclamation has been in deeper water, in more environmentally sensitive zones, and under stricter scrutiny than the last. The 1960s methods, essentially just dumping fill material, are no longer acceptable. The seafloor is a living ecosystem. Monaco sits between 2 marine protected areas, the Larvotto Marine Reserve to the east and the coralligenous of Spélugues to the south. These aren't just regulatory lines on a map. They're real functioning ecosystems. The Larvotto Reserve alone shelters over 60 species of coral and vast meadows of Posidonia oceanica, a seagrass endemic to the Mediterranean that grows only 1 centimeter per year and takes centuries to recover if damaged. A botched construction operation could cause irreversible harm. So when Prince Albert II revived the idea of a new offshore extension in 2013, a project first proposed in 2006 but abandoned due to the financial crisis and environmental concerns, the engineering brief was extraordinarily demanding. Let's talk about the actual site. The Anse du Portier, which literally means the Gatekeeper's Cove, is a small bay between the Grimaldi Forum Convention Center and the Fairmont Hotel, made famous by Formula One's hairpin corner. The water depth here varies but reaches around 25 to 30 meters. You're not placing a structure on a beach, you're building in the open sea. There are 3 fundamental engineering problems to solve when you build a land extension like this. 1. How do you create a stable perimeter wall that can hold back the sea permanently? 2. How do you fill in that perimeter with materials stable enough to build on? 3. How do you do all of this without destroying the marine ecosystem you're surrounded by? The answer to problem 1 is a structure called a caisson. A caisson is, at its simplest, a large, watertight, hollow concrete box. But these aren't boxes like you'd picture. They're enormous, precision-engineered structures. For Mareterra, 18 caissons were fabricated. Each one stands approximately 26 meters tall. That's the height of a 7- or 8-story building. And each one weighs roughly 10,000 tons. That's the equivalent of about 1,600 African elephants per caisson. But here's the key concept. They're hollow, they're cellular. Think of a honeycomb structure scaled up to building size. The caisson is divided internally into a grid of cells. some of which will eventually be flooded and filled with material for ballast, others left as chambers. Why hollow? Because if you make something that massive out of solid concrete, it sinks immediately under its own weight during construction. The cellular structure means you can control buoyancy, you can float the thing like a ship. These 18 caissons were fabricated in the port of Marseille, about 200 kilometers west of Monaco along the coast. They were built using a technique called slip forming, where concrete is continuously poured and the formwork rises slowly upward at the same rate, producing a seamless vertical wall of reinforced concrete without construction joints that could be weak points. The concrete itself is a special marine-grade mix designed to resist chloride ingress, that's salt ions penetrating the concrete and corroding the rebar, sulfate attack from seawater, and the freeze-thaw cycles that batter any structure at the waterline for decades. Once complete, each caisson was floated, yes, just like a ship, and towed across the Mediterranean by barge to Monaco. Before a single caisson arrives, the seabed has to be prepared. And this is a step that many people overlook, but it's arguably the most critical phase of the entire project. You cannot just sink a 10,000-ton concrete box onto whatever happens to be on the ocean floor. First, dredgers removed the top layer of seabed sediment, the soft silt that accumulates over centuries. You need to expose solid, competent material underneath. This had to be done carefully. Disturbing too much sediment would spike turbidity in the water column, blocking sunlight from reaching the protected Posidonia seagrass beds nearby. The team used underwater anti-turbidity screens, essentially giant fabric curtains suspended in the water column, to contain the sediment plume and monitored turbidity in real time with a network of underwater sensors. Once the silt was removed, here's where it gets technical. The seabed is not perfectly flat, and you need your caisson, which is essentially a rigid rectangular box, to sit on a perfectly level foundation to within incredibly tight tolerances. The team used a technique called vibrocompaction, inserting vibrating probes into the seabed material that rearrange the granular particles, closing voids and increasing density. Think of it like tapping a container of sand to make it pack tighter. This creates a more competent, less compressible foundation. Over this, a layer of granular material, precisely graded crushed rock and gravel that was laid by a specialized vessel. This forms what engineers call a rubble mound bed, a leveled, compacted blanket that distributes the load uniformly and gives the caisson a stable platform to rest on. Now, the moment of placement. Project director Christophe Hersinger of Bouygues Travaux Publics described it this way. You have to set the position of the caisson with about 100 millimeters accuracy in each direction. That's 10 centimeters of tolerance for a 10,000-ton structure floating in open water. In the Mediterranean, with swells and current. This is done using GPS positioning systems, tugboat coordination, and a team of divers below who verify contact and alignment. The caisson is slowly ballasted. Water is let into some of the cells to decrease buoyancy until it settles precisely onto the gravel bed. Once down, quarry ballast rock is immediately dumped around the base to lock it in position. The caisson cells are then progressively filled with sand and concrete grout. All 18 caissons were placed between October 2017 and September 2019. The last one closing the perimeter belt near the Grimaldi Forum in September 2019. The shape of the belt is deliberately curved, not rectangular. Architect Denis Vallaud designed it to follow the natural flow of the Mediterranean current along that coastline, reducing turbulence and flow disruption in the water around the structure. This is a perfect example of engineering and architecture actually informing each other. The curve isn't just aesthetics, it's fluid dynamics, wave energy, and the Yarland chamber. Here's a structural detail that I think is genuinely brilliant and underappreciated. On the seaward side of each caisson, the face that takes the full force of Mediterranean swells, the design incorporates what's called a Yarland chamber. Named after engineer Pierre Yarland, who developed the concept in the 1960s, a Yarland chamber is a perforated front wall with a hollow cavity behind it. When a wave hits, instead of impacting a solid wall and generating maximum pressure, the water partly flows through the perforations into the chamber. The chamber absorbs and dissipates the wave energy, reducing the peak forces on the caisson by a significant margin. Think of it like a crumple zone in a car. You're trading peak force for energy dissipation over time. In engineering terms, the caisson wall must resist two types of wave loading: quasi-static pressure from sustained swells and impulsive pressure from waves that trap air and slam. Impulsive loads can be many times higher than quasi-static ones. The Yarland chambers specifically target that impulsive component. Anti-seismic design. The French Riviera sits near the intersection of the Eurasian and African tectonic plates. Seismic activity here is moderate but real. Historical earthquakes in the region, including the 1887 Ligurian earthquake, one of the largest in that area's history, caused damage across the coast. Mareterra was designed to anti-seismic standards. For a caisson structure sitting on the seabed, seismic loading presents a very specific engineering challenge. The caisson and the soil beneath it respond differently to shaking. The heavy, rigid concrete structure has inertia. It wants to stay still while the ground moves under it. This creates sliding and overturning forces at the caisson foundation interface. The design accounts for this through the weight and geometry of each caisson. A heavier, wider base resists sliding. The rock armor placed around the foundation, which provides lateral confinement, and the grout filling of the cells, which increases mass. The entire system is designed so that even under the region's maximum credible earthquake, the caissons don't translate, rotate, or allow the structure above to lose integrity. With the caisson belt complete and sealed, you now have a watertight perimeter enclosing a lagoon, a pocket of sea enclosed by concrete walls. Now the real volume filling begins. 750,000 metric tons of sand were pumped and placed inside the caisson belt. To put that number in perspective, that's roughly the equivalent of filling 300 Olympic swimming pools with solid material. The sand came by ship. Marine logistics was a deliberate choice. The project director specifically noted that using sea transport minimized local disruption to Monaco's already congested road network. At peak activity, a construction vehicle arrived at the site entrance on average every 5 minutes. The team built their own dedicated concrete plant on site, producing at 70 cubic meters per hour, eliminating 40 to 80 concrete mixer truck trips per day through Monaco's narrow streets. Over the sand fill, a reinforced concrete platform slab was poured, the structural deck that everything above sits on. This is where the connection between marine engineering and conventional structural engineering happens. The platform must distribute the loads from buildings, roads, trees, and people down through the sand fill and into the caissons. At the base of the caissons, an underwater rock armor slope was formed, a graded stone revetment that prevents storm-driven seas from eroding the granular material supporting the caissons. This is your last line of defense against progressive foundation failure. This is the part that genuinely sets Mareterra apart from any previous land reclamation project at this scale. Before construction began, marine biologists and divers spent 9 months relocating 500 square meters of Posidonia oceanica meadows from the construction zone, transplanting living seagrass to the adjacent reserve areas. This wasn't legal box ticking. Posidonia is an ecosystem engineer. It oxygenates water, filters sediment, and provides nursery habitat for dozens of species. Losing it means losing the whole food web that depends on it. The caisson surfaces themselves were engineered for ecology. Rather than smooth concrete, which marine life struggles to colonize, the caissons were given grooved, textured surfaces. These microhabitats mimic natural rocky substrate, giving algae, invertebrates, and eventually fish the foothold they need to establish communities. The caisson belt has been deliberately designed to function as an artificial reef. Anti-turbidity screens were deployed throughout the dredging and filling phases to contain sediment plumes. Noise monitoring was continuous. Construction schedules were adjusted in real time when sound levels threatened to disturb shellfish colonies in the adjacent reserves. Since construction, marine monitoring programs have documented a measurable increase in fish biodiversity around the new infrastructure. The caissons are working as habitat, not just as walls. Mareterra opened on December 4th, 2024, 6 months ahead of schedule. Inaugurated by Prince Albert II and Princess Charlene. The district covers 6 hectares of what was open water. It contains 5 buildings with 130 apartments, 10 waterfront villas, a 30-berth marina, a 10,000 square meter extension of the Grimaldi Forum, over 4,000 square meters of retail, and more than 50% of its surface dedicated to public space, parks, promenades, and plazas. The centerpiece building, Lorenzo, designed by Renzo Piano Building Workshop, rises 60 meters, 47 luxury apartments. The total project cost, approximately 2 billion euros. That's roughly 333 million euros per hectare of new land created. For context, the entire island of Manhattan is about 5,900 hectares. If you were to create Manhattan from scratch at Mareterra's cost per hectare, it would run to approximately 1.96 trillion euros. Land reclamation, at this level of engineering and environmental care, is extraordinarily expensive. But for a sovereign state with no other direction to grow, it's not optional. It's existential. If you haven't seen the first video on the Torre Latino in Mexico City, go check that one out. Another incredible piece of structural engineering with some really counterintuitive physics. See you in the next one.